Good morning, everyone. Welcome to lecture 12 on finite element method. So a little summary of what we have done so far or the journey that we want to, to have together. We mentioned that the starting point of a finite element method is basically a differential equation, and we call that differential equation in this setting a strong form. And the first step is to transform that to a weak form, and then we want to solve the weak form. This is the first step, and that is what we have been busy with in the previous lectures, and that's what we are going to do also still in this lecture. We also mentioned there are different types of approximations inherent to the finite element method, so we talked about those, and also we mentioned this fairly simple strong form. So it's a differential equation. It's a second order differential equation, a very simple one with some prescribed boundary conditions. In this typical case, on the left-hand side of the domain, you have a Dirichlet type boundary condition. On the right-hand side, you have a Neumann type boundary condition. But we also, if you remember from the previous lectures, we also mentioned that although this looks like a very simple second order differential equation, you may have a good feeling that this is a very meaningful differential equation from a mechanical perspective, because it also relates to the, let's say, to the balance of a one-dimensional mechanical structure. So let's say you have that strong form, and now you want to derive the weak form. In order to derive the weak form, the first step is to define your test functions, how you want to test your strong form, basically. And for that, we use a particular family of these test functions. We remember the test functions should be arbitrary, they should be continuous, and they should be zero at Dirichlet type boundary conditions. And then on top of that, you need to define a space for them. So you have to say whether they are linear or quadratic or something like that. But that is something we want to discuss later. But the key properties of that test function is here. They multiply your differential equation by that test function. You integrate that. You do this integration by part, which basically comes from this formula. And then if you go through the integration, you end up with this form, which we can also write it like this. And then inserting the boundary conditions from your prescribed conditions, you can exactly distinguish these three types or three parts in your weak form. There is internal contribution over the domain. There's external contributions over the domain, in the sense that these are inside the domain. Usually for us, they are zero if it is zero, obviously. And then you have these external contributions that are on the boundary of the domain. And to be more specific, to be more concrete, we thought, let's look at a particular function. So instead of f, let's just use 1, for instance, to make it simple. And then let's solve this using the finite element method. This is a very nice function because basically it could relate to that gravity problem that we talked about. So if you have a bar under gravity, that whether it is elongating or shortening or compressing, it is a similar differential equation, but also we have an analytical solution for this. So it gives us a nice benchmark to start with. So we know this is the analytical solution. It's a quadratic polynomial. Now we derive the weak form for that, and the weak form for this particular boundary conditions, it ends up like this. So we have the strong form here, and we have the weak form here. So from this point on, we pretend that we don't know what is the analytical solution. we assume we just have this, it's a weak form. And from that weak form, we want to calculate the approximate solutions. So we did these. So we included, let's say, 5 different ways of approximating it. Today, we want to extend that idea and include 5, 6 more. Just to remind you, a simple approximation would be, for instance, a one-piece linear approximation, in a sense that you just want to approximate this thing with one piece, and then you get this line. Then the other one was, let's say, a two-piece approximation, two-piece linear, but it is uniform in the sense that the point is exactly in the center. And then if you go through the procedure as we did together in the last lecture, you can find the coefficients corresponding to those. The key step here was this. So at some point in your derivations, you end up with something like this. And this equation looks like one equation, two unknowns, but it is actually not, because you know that it should hold for any C1 and D1. So basically you can think of it like this, that you just take two specific pairs, and for that you just get two equations, then it becomes a two equation, two unknowns, and you can solve that system. So this is, I think, the only, let's say, trick that you need. Okay, so you do that, and then basically when you calculate it, you end up with something like this. It shows that, again, your approximate solution hits the analytical solution. Now, we also extended that to a non-uniform setting, assuming that the point that you are picking is not exactly in the center, so it is on the right-hand side of that domain. So if it is on the right-hand side, then you get this one. It's still doing a very similar thing. If you now pick that point to be on the left-hand side of the center, you also go through a similar procedure, but also you get again, the answer here. I don't know if you can see it, but you also get the answer here. So eventually, it doesn't matter which way you do this. It turns out that you always get, let's say, what we call super convergence. You always get exact result at the nodes, depending on where your nodes is. Of course, that point can change, but wherever that is, you get that exact result. But also importantly, if you remember, I mentioned that you should think that, or you should remember that usually what happens for you is that this exact result doesn't hold. So, I mean, if you look at this picture, this is kind of underwhelming, because, well, if you have the exact result, these are just a few points, but the reality is more like this. So basically, you don't know where the result is, but now, because of what you did, you can at least identify a few, let's say, discrete points on the solution. Okay, so this would be your approximate solution, these red points. Okay, or if you want, you can also connect them and then think of this one as the approximate solution or something. But and the important thing is to remember that we usually solve a differential equation for which we do not have an exact solution. Okay, so that now that we have done one piece and two piece uniform and two piece non-uniform 1 and 2, I mean, you can of course keep playing this game for many other non-uniform two pieces, but then we thought, well, why don't we just make it a generic, assuming that point is not, I mean, we don't say it is exactly center or right or left, we just say it is at any distance a, where a is somewhere between 0 and 1. So we do that, we play exactly the same game, we come to this equation after some mathematical steps and manipulation, And then you also get your generic solution for any A. And of course, once you have this, you can now set A equals 1/2, and then you recover what we did for two-piece uniform. You can set A equals 0.6. Then this would be recovering what we did for two-piece non-uniform. Well, the point was on the right, and then this was the point was on the left, the non-uniform too. So we have done this. Before I go to the next part, which is let's say a three-piece linear approximation, I just want to come back to the picture we had and give you a different view on this. I don't go into details, but I think there is something you should think of, or you should have in mind when you do finite element method. So I'm going to remove these. And let's say we are asking ourselves if we can represent these graphs somehow differently to indicate the nature of our approximation procedure better than these do. Okay, so let's say we have these. What I want to draw now is to, maybe I just duplicate the same shape. Okay, so let's say this is the graph. I'm going to remove the little x here. Yes, so this is the graph. Now on the left hand side, you have your u with respect to x. On the right hand side, what I want to do is to have u prime with respect to x. Okay, so that's what I want to do. Let's see, or let's think what happens to u prime. And in order to do that, I'm going to remove these lines that we had. Okay. So let's think about these lines exactly, but now in terms of u prime. If you remember the analytical solution, we did it at the beginning, or we had it at the beginning. So the analytical solution is this: is u equals minus 1/2 x squared plus x. So u prime would be minus x plus 1. Okay, so if I come back to that slide, we know the analytical u prime so again, remember here the analytical solution is minus 1/2 x squared plus x. So the analytical u prime would be minus x plus 1. So if you want to draw minus x plus 1, it's going to be a line with the slope minus 1, which is passing through the point 1, 0. Okay, so it would be your u prime. Okay, so this is your analytical solution for u prime. Now, if you think of the, let's say, the orange curve, the orange curve is the one corresponding to 0.5. So that is a two-piece uniform. And if you remember, for a two-piece uniform here, we have the slopes for each piece. So it is 3/4, this is 1/4. In other words, you can think of it this way, that for the orange one in the first piece, again from 0 to 0.5, that u prime is, let's say, 3/4. So it's going to be something like this. It's constant. Okay, maybe I make it a bit thicker to have it more clear. It's constant and it's 3/4 exactly. And then for the second piece, it is constant and it's 1/4. So it's going to be somewhere here, maybe. All right. Now, before I make this picture too complicated, I want you to see it this way. If you look at these areas, it seems they are canceling each other, basically. Okay, so this is in the heart of the finite element method, basically. We don't look at it from that perspective, but this is kind of what is happening here. Okay, that area is, let's say, some sort of approximation of error for you, and then canceling that is the way, or is why, or how the finite element works. Okay, you can play the same game for the other ones. So for instance, if you think of any of them, if you think of this one now, it would be 0.7. Then for the second piece, it would be 0.2. So the other one, it would be 0.7, so slightly less in the first half. So it's going to be somewhere here, and then also 0.2, slightly less in the second half. So somewhere here, maybe. If you do it for the blue line, same thing, but now in the opposite direction, so slightly more if you want. So it's going to be somewhere here. And then in the second piece, it's going to be somewhere here. Okay, but then again, if you play that little game that we talked about, if you think of those areas, in each case, you can see that the areas basically are canceling each other. So if, I don't know, if I want to repeat this picture and clean up, let's say, the orange part and the blue part, now you have this one, but then the same story holds. So you see always these little triangles canceling each other. Okay, so how can we see this? It's actually not too difficult, because we have now the generic solution. So remember, here you have the generic solution. So from the generic solution, you can actually calculate u prime for each piece. In other words, if I just take this generic solution and duplicate that, then you can show that for the first, yes, you can show that u prime for each part is calculated like this. And basically now you have the u prime as a function of a. And then you can draw that graph that we just had in its generic form. So you can just basically draw a graph which would look like this, let's say U prime X, and then that graph, you know, the analytical solution is, let's say, this. So we have the analytical solution. And now for any A that you insert in this, you can play the same game basically. So I don't know, let's say if A is somewhere here, you would play the same game. Okay, so you can think of sorry, let me just let's say if A is here. So if for instance A here, then you would have also these two pieces again. So you'll have that little triangle, this one, and then okay. And these slopes are exactly, this is 1 minus 1/2 of A, and let's say, or the value of them basically. So I'm talking about U prime, and that would be 1/2 minus 1/2 of A. Okay, so this is again somehow the way how the finite element works. So maybe thinking of the derivatives is not such a bad idea. And it's not very surprising because you can see in your weak form, you are actually playing with the derivatives. So it's a derivative-based solution. So instead of dealing with the second derivatives, you are dealing with the first derivatives. Okay. But also, okay, this is another thing. If you just look at it, you can imagine or you can think that finite element usually underestimates the analytical solution. So you always get a solution that is less than the analytical solution. If I want to show that, maybe you can think of also this picture or any of the pictures we had previously. You see, if this is your analytical curve, your finite element pieces are under the graph. They are not above the graph. You can imagine that, I don't know, if you wanted a two-piece approximation, maybe this would have also been an approximation. Okay, so you can have different two-piece approximations, but finite element ones, they are usually, or the way we do it at least, is usually relating to or related to underestimating the analytical solution. So maybe I also put that here in a little note, maybe somewhere here, that FE solutions seem to, I don't want to say it's too strongly because I'm sure you can find different ways to handle this, seem to underestimate the analytical one. Okay, so there is a saying in the community that finite element solutions approaches the analytical solution from below. So this is kind of the equivalent of that. So it is always below the analytical solution, if you want, in that sense. I'm also writing that. But this is a very sloppy way of explaining it, but I think you get the idea. So FE solution approaches Again, you can prove it, but let's say for the way we do it, you can prove it, but for us, at least visually, you can see it. We don't talk about that in any more details. Okay, so now let's go back to our problem. What we want to do next is to go to a different approximation. So we have one piece linear, two piece linear for different points. Now we want to do three piece linear uniform approximation, and then we want to do three piece generic. So three piece linear, I am going to, let's say I'm going to skip this. I keep this as an exercise for you. And the reason is the following. The next one is three piece generic. So if we manage to do three piece generic together, then of course you can assume that those pieces are exactly, let's say, in 1/3 and 2/3, the two pieces that we talk about, and that would be a simpler step for you to recover. So you can do it as an exercise, and then as a particular case of the generic case, you can also test your solutions. Okay, so let me just come back to this, and now we do the three piece. If your microphone is on, may I kindly ask you to mute it if you don't want to speak, please? Thank you. Okay. So what we want to do next is, let's say, three piece generic. So I just changed that 2 to 3, and then again I just explained this. Three piece linear, three piece uniform would be this. So you have 0, 1, 1/3, 2/3. What we want to do now is three piece generic. So this is 0, this is 1, this is any A, and this is any B. Obviously, the constraints are that A should be between 0 and B. And then let's say B should be larger than A and 1. Okay. So this is what we want to do now together. So I'm going to just remove the generic one. Now we have this little piece. I will just put here on the corner so that we remember that is what we meant. That is what we mean by A and B. Okay, so the procedure is very similar to what we have done for a two-piece linear approximation. What you need to do and what we want to do is to write those test functions and use for each of these pieces. So you would say if X is from, let's say, 0 to A for the first piece, if X is from A to B, second piece, and if X is from, let's say, B to 1, in the first piece, let's say W is C1X plus C2. So we do linear approximation. So each of these, as you can see, are linear. U1 is F1X plus F2. Then W is D1X plus D2. U is G1X plus G2. Obviously, you don't W is then E1 x plus E2, and U is here H1 x plus H2. So if you look at this, you have, again, just theoretically speaking, you have 6 unknowns here, F, G, H, 1 and 2. You have 6 unknowns here. The ones here are not too bad because later we know it's going to hold for any W. That means it's going to hold for any C1 and C2 and so on. So, and these ones are not really unknowns. These are just the coefficients that they can be arbitrary, but also they need to satisfy the conditions that we wanted to have. So for instance, you know that at 0, we have a Dirichlet type boundary condition. So that means if X is 0, W must be 0. So when this is 0, this is also 0. That means C2 must be 0. So that's a condition, for instance, that you need to satisfy. Another condition you need to satisfy is the continuity between them. So this we just talked about. The next condition is continuity. So continuity basically tells you that at A, whatever you get, let's say you would have a function which looks like this. So at these points, at points A and B, you can have different pieces of lines. So we call them piecewise linear or pieces of lines. But at those points, A and B, they must be continuous. That tells you that D2, for instance, must be A times C1 minus D1. Okay. And then if you play the same game, then E2 must be B D1 minus E1 plus A C1 minus D1. Okay, so it's not bad basically. Now this is 0, and these two are expressed in terms of the other ones. So in fact, you have only 3 variables or 3 coefficients, which again, they must be arbitrary. So at some point you should impose that condition, or you should remember that eventually whatever happens is for C1, D1, and E1. Okay, so this is the first part. Now we played a similar game for the U part, because U at 0 is 0. So if you put this X equals 0, then U is 0. That means F is 0. So F2 is 0. Sorry, F2 is 0. Again, G2, because U also should be continuous, so you don't want to have a jump of displacement at nodes, obviously. Then this would be F1 minus G1. And then H2 would be B G1 minus H1 plus A F1 minus G1. Okay, so now again, if you look at this, you have 3 unknowns. So again, G2 and H2 now are expressed in terms of the F1, G1, and H1. Okay, so basically, when you think about this one, you can imagine that these are unknowns. So what is F1, what is G1, and what is H1? So we need 3 equations to solve for this, and we will come to that. Okay, so this is the first step, and then again, I don't know how much of the previous lecture you can remember, but what we do here is exactly what we did previously. Remember, if we had a 2-piece approximation, we did exactly the same thing. We had these 2 pieces, then we defined this continuity condition and boundary conditions. Then we split the weak form into those two pieces, and then you get your equations, or you get this big equation. And because they hold for any coefficients, they give you two equations, two unknowns, and you can solve it. So this is the same story. Now it is just three pieces. Okay, so we do this. Now, assuming that we have all of what we just discussed about, let's clean up. Let's clean up this part and write the weak form. Okay, so we know this. I'm gonna keep this little part here on the corner. Maybe in the video it doesn't look very well, but in the PDF file you have a higher quality of this anyway. So that's that. And then what you want to do is now to use this integral, your weak form, split that weak form into three pieces, do the integration by inserting the values that you have here into those integrals, and that's it. That's all you have to do. So that integral up there, we are going to split it into the first region from 0 to a. That would be wu prime dx plus from a to b wu prime dx plus b to 1 wu prime dx. And then the same thing on the right hand side, 0 to a w dx plus a to b w dx plus b to 1 w dx. All right. Now, it shouldn't be too complicated to calculate this. As you can see from the functions above, I'm going to write those things. So w prime in the first region from 0 to 1, this is just C1, right? U prime is F1. In the second region, W prime is D1, U prime is G1, then E1 and E1 H1 in the third region. Now here in the first region, W is C1X. In the second region, W is D1X plus A times C1 minus D1. This is exactly what you had here. And this W would be basically W you are going to have here, or you had here. So in the last region, let's say W would be E1X plus B D1 minus E1 plus A C1 minus D1. All right, now that you have this, all you have to do is to do the integration. I'm going to skip that intermediate step. It's just a very simple integral. You can do it also as an exercise. And if you do that, I write, or I tell you what's going to happen basically. So this is again your weak form now. If we write that, we end up with an equation which would look like this. It's going to look similar to something like C1 times something plus D1 times something plus E1 times something. That equals 0. Okay, so equals 0 because let's say whatever is here, I also brought it, or I bring it to the left hand side. Now, in these expressions, in these three dots, you have relationships which are related to F1, G1, and H1. Okay, and then you play exactly the same game as we played before. This looks like one equation and many unknowns, but it's not that bad because this has to hold for any C1, D1, and E1. Okay, and then again, let me just remind you of one of these that we have done before. For instance, we had something like this. So you can see that in that portion, the coefficient that was inside C or in front of C1, it was related to E1. The coefficient in front of V1, it was related to F1. It's a similar story here. So the coefficient that you have here in front of the first one, the C1, it's going to have some relation with F1. So that gives you F1. This one gives you G1. Let me just use a different notation kind of. I don't mean the expression is exactly F1. I just mean that if this thing is 0 and it holds for any C1, D1, and E1, then basically what you can imagine is that this must be 0, this must be 0, and this must be 0. Sorry, this must be 0. Okay, so but by doing that, you get three equations. Let me write that clearly because I think that's a key step here. So eventually, having said all that, you get this equation that has all the information for you, or all the information about the coefficients. But then again, because it holds for any C1, D1, F1, now this first part, it gives you one equation in terms of F1. The second one, this gives you another equation. So let's say it's like that. It gives you another equation, let's say another function. Now, in terms of G1 is 0. And then the last one, it gives you, let's say, another function in terms of H1 is 0. So now you have basically three equations, three unknowns, and then you can calculate F1, G1, and H1. Again, I call it three equations, three unknowns, because it is what it is in its most generic form. For you, it is actually three single equations or three individual equations for three individual unknowns. You don't have, it's not a coupled system necessarily for you, or in this case, it's not. But eventually, if you do that, you can calculate F1, G1, and H1. And I'm going to write them in the next slide. or in a separate slide to have everything there. Okay, so this is basically the key. You have eventually 3 equations, 3 unknowns if you want, because you can play with these coefficients. You can assume that, for instance, in order to get this one, in order to get the first one, here, you can assume D1 is 0, E1 is 0, C1 is 1. Okay. So that gives you the first one. The second one, if you want, then you assume D1 is 1, E1 is 0, C1 is 0, something like that. You can assume each of those coefficients is 1, the other ones are 0, and then you get that. All right, so this is what we had. From the, let's say, the equation, the weak form. Now, I'm gonna omit the weak form itself. We will have this equation which should hold for any C1, D1, and E1 because of arbitrariness of W. Again, just remember this relates to the arbitrariness. And if you do that, you can see that F1 would be 1 minus 1/2 A. G1 is 1 minus 1/2 A plus B. And H1 is 1 minus 1/2 B plus 1. Okay. So this is not too bad because now you have everything you wanted. So remember, the key here is to calculate U. U is the displacement that you are looking for. And if you remember, we said we have only 3 unknowns, F1, G1, H1, and now we have them calculated already in terms of, let's say, A and B. So you have everything you need, and you can insert this in U, and you can calculate your displacement field. So I want to generalize this even further after the break. So let's have a little break now. It's 9:21. So let's say, a 9-minute break. We continue at 9:30 sharp. All right. So we are back, and as promised, what I want to do next is to insert these solutions into the displacement function itself and play the same game with it. So let's plot it and see where we are. Okay, so I'm going to remove this intermediate step. So the W here, it's no longer needed. What you can see here is very simple. Now, for each of these pieces, you have a U, and for each of those, you can clearly have their coefficients. So what we want to do is to write this displacement function as let's say, a piecewise linear function or a 3-piece function. That's what we are going to do. So let's say we can say U equals 1 minus 1/2 A times X in the first piece. Again, see, this is Fx or F1x, F2 is 0, and F1 is 1 minus 1/2 A. So I'm going to just put it there, and that is U in the first piece. So this is the game I am playing. Okay, so we don't need this anymore. In the second piece, U is now G1x plus G2. G2 is itself A times F1 minus G1. And if you insert that, you would end up with something which looks like 1 minus 1/2 A plus B times x plus 1/2 a times b. And eventually you insert h1 for the third piece of u. So for the third piece, you have u equals 1 minus 1/2 b plus 1 x plus 1/2 b. And as I mentioned, the first piece is basically x is 0, x is in 0 and a. The second piece corresponds to x between a and b, and the third piece is corresponding to x between b and 1. All right, so now that we have this, let's maybe write them a little more compressed. So you have this very nice, let's say, 3-piece function, and that is what we wanted to have, right? So this was sort of the expectation for this exercise. But also, if you just look at it visually without thinking too much about it, you can see there is some sort of uniformity in this. So if you think of this piece, for instance, and compare it to these two, it has some similarities. So it seems that A and B are the two ends of a piece that you are working on. So if these two ends are B and 1, basically you get B plus 1 instead of A plus B. If these two ends are 0 and A, then you get 0 plus A, which is just A. Okay, so it seems that this is a generic form, and then the same holds for 1/2 of AB. So if you think this is 1/2 of A times B, now here it would be 1/2 of B times 1, and this would be plus 1/2 of 0 times A, which is 0, so we don't have it. So it turns out that you can also write this thing as one unified format, and that is, I think, very nice. So you can just generalize this and say, well, U is 1 minus 1/2 of, let's call it alpha and beta, times x plus 1/2 of alpha times beta. And that could hold for any alpha and beta. So if alpha beta, let's say if the set alpha beta is 0 and A, then you recover exactly what you had up here. If alpha beta is between A and B, then you recover this one. And if alpha beta is B and 1, you recover the last one. Okay, so now this is very nice because this holds for any alpha less than beta, and that is less than 1, and that is larger than 0, basically. So you can think of a piece of your displacement solution to be like that. All right. Now that we have this generic form, let's think of a specific example for this. So let's think of a case where A is 0.4 and B is 0.6. Okay, so if you have that, and I'm going to just write the same functions that we have up there. So the first function would be u equals 1 minus 1/2 of a, that would be 1/2 of 0.4. So that would be 0.8 x. That is the first piece, if x is between 0 and 0.4. Then for the second piece, you have 0.5 x plus 0.12. All right. And that would be x between 0.4 and 0.6. And then eventually, if x is between 0.6 and 1, then u is 0.2x plus 0.3. Okay, so this is basically a particularization of what we have up there for our specific domain here. Now, why do I do this? Because I want to also, like we did before, I want to compare this with our approach to what we had in, let's say, two-piece linear, and I want to compare it with the analytical solution. So you have this. And basically that means if you now think of your analytical solution again, let me just pretend drawing the analytical solution. So if this is the, if this is the vertical axis, let's say for displacement for u itself, and this is maybe x. The analytical solution is a quadratic solution again, as we discussed before. It looked like this. Okay, so that was kind of the analytical solution for this problem, I think. Now, what you want to have is to draw the solution that you have, the piecewise linear solution, and you have a three-piece solution on points that are 0.4 and 0.6. So if you look at those, you get a function which looks like this. Okay. So this would be your three-piece function, the red one. But then again, most or more interesting than the function itself is to look at its derivative. So if you think of the derivative of that function, or the derivative of the analytical function, remember the analytical solution here is u equals minus 1/2 x squared plus x. So if this was u versus x, now u prime versus x is minus x plus 1, as we discussed before. So that would, let's say that would be a line like this. So u prime is minus x plus 1. And now if you look at the derivatives of your function here, it's 0.8, 0.5, 0.2, corresponding to those three pieces. So let's say the first piece is from 0 to 0.4. So if you assume this is 0.4, and this is maybe 0.6 here. So let's say this is 0.4, This is 0.6. This is maybe 1. This is 0. Now, if you look at that, between 0.4 and 0.6, the slope is 0.5. So it's going to be something like this. So you get that little triangle. And then here it would be 0.8. And then down there it would be 0.2, something like that. So then again, you see these little triangles canceling the areas of each other corresponding to the analytical solution. Okay, so this is also your three-piece linear function. All right. Very good. So that's what we wanted to do. Now let's go back to our, let's say to our menu that we started at the beginning. We had this strong form. We derived the weak form. We want to look into different approximations. We had done one piece. We had done all the two pieces. Now we did also the three piece. We did the generic form. So from that one, you can also get the uniform one. Now, again, four-piece linear uniform, I keep it as an exercise for you. But what we will do together is the generic form of it. So we do four-piece linear generic, and then again, once you have the generic version of this, let's say the specific version, the uniform version is not complicated at all. In order to do that, we do exactly as we did for the previous one. Let's say you start with this, but now instead of A and B, we want more pieces. So we are looking for a four-piece approximation. So basically what that means is that the range between zero and one would be split into four pieces. So let's say this is 0, this is 1. Then we will have A, B, and C. Okay. Again, obviously, A must be larger than 0, B must be larger than A, C must be larger than B, and C must be smaller than 1. Okay, so this is what you want to do. All right, the process is exactly identical to what you did before. It's just slightly longer because now you have to impose these continuities and they look slightly longer than the previous version, but it's basically the same thing. So you would say if X is between 0 and A, then W is, let's say, C1X plus C2. U is, let's call it G1X plus G2. Then you do the second piece between A and B. X is between B and C. X is between C and 1. Each of these pieces is just a very simple linear piece. I1x plus I2, and U is J1x plus J2. So the next step is to impose the conditions that you have. So you need to impose your boundary conditions and continuity conditions. From those boundary conditions, for instance, you can see that G2 would be 0, C2 would be 0 because it's Dirichlet, and then D2 would be like A C1 minus D1 because it must be continuous. So if you do those, you also get these additional relationships, and I'm going to write them separately because it's longer than the previous version. So let's say you have these functions. Now, imposing those constraints, they give you additional information on this. So you would know that, for instance, C2 and G2 would be 0. So those are the simple ones. Let's get them out of the way. So G2 is 0, C2 is 0, that we get them from our, let's say, the Dirichlet condition, Dirichlet boundary condition at 0. But then for W, you also introduce this piecewise continuity between each piece. So you get D2 equals A times C1 minus D1. E2 equals B D1 minus E1 plus A C1 minus D1. F2 equals C E1 minus F1 plus B D1. So this is the longest version we have, obviously, but I'm intentionally doing this to show you the sort of the repetitive structure, because as I mentioned, a part of this course, or part of the idea of having a finite element code, is that at some point things get sort of repetitive, and you can program this. You can find a nice algorithmic approach to almost everything in this course, and that is why, or that is how we will be able to program this later. So also, another reason this is long is that it's a generic form. So if you had numbers here, obviously these numbers would be, I mean, so this expression like H1 minus I1, this would be something like 0.1 or something. So it would be much shorter to just write them like that. Okay, so anyway, you would have these. So again, now if you look at what you had previously, this was 1, 2, 3, 4, 5, 6, 7, 8 unknowns here, and then 8 of them here. So maybe you can think of them as 16. But as we said like before, first of all, these are not unknown because these are arbitrary, but also they should satisfy their conditions. So D2, E2, F2, they relate to C1, D1, E1, F1, as we have it here. C2 is 0. So basically they are not 8, they are 4. But these 4 are also arbitrary. So C1, D1, E1, F1. That's this 4. Here, also we are dealing with 8. This one is 0. The other 3 are expressed in terms of the first 3. So you would have now 4 unknowns. So basically you would have 4 unknowns. We need 4 equations to capture them. And in order to get those 4 equations, we play our famous game. We do exactly as we did before. We are going to write the weak form in terms of these 4 pieces. But obviously I do it shorter than before, so I don't go into details. But eventually what happens is that you would just write your, let's say, W prime, U prime, instead of 0 to 1, from 0 to A, then from A to B, then from B to C, and let's say from C to 1, and that would be equal in integral from 0 to A W dx. All right, and now for each of those pieces, it's super simple to just insert their corresponding values. So for instance, here you can see that W prime would be C1, U prime would be G1. Okay, so you can just insert the values for these. If you do that, then you get also your longer equation, or that four unknown relationship that we want to have. So this would be your weak form, basically. Now, if you play this weak form, if you do the integration, you would end up with a relation which again looks like something like it's going to look like some function of G1 times C1 plus some function of H1 times D1 plus some function, okay, maybe I call it F, and I call this F star, and then I call this F double star of I1 times E1 plus, let's say, F triple star. These are different Fs, different functions, and J1 times F1 equals 0. Okay, and then this is the same thing, because this holds for any C1 and D1 and E1 and F1, you can calculate those coefficients from this. Okay, so this is what's going to happen. This integral should hold for any C1, D1, E1, F1. And if you play that game, you can calculate the coefficients, and they will be as follows. G1 would be 1 minus 1 over A. H1 would be 1 minus 1 over A plus B. I1 is 1 minus 1 over 2 B plus C. And eventually the last one, J1 is 1 minus 1 over 2 C plus 1. Again, you see that sort of unified coefficient structure here. And what we want to do next is to insert these coefficients into their corresponding U's and write this, let's say, write the analytical solution eventually. Sorry, the approximate solution, not the analytical solution. The solution for displacement based on the coefficients that we have here. So again, remember we had this functions. So these, we have the u's here, and now you have their coefficients individually. What I want to do is to write those functions separately. Okay, so if you do that, then u, the first part would be 1 minus 1/2 of a times x. That would be for the first piece. The second piece would be 1 minus 1/2 of a plus b times x plus 1/2 of ab. The third piece is 1 minus 1/2 of b plus c plus 1/2 of bc. And the last piece is 1 minus 1/2 of c plus 1 plus 1/2 of c. Okay, so now you see exactly the same game or the same structure as we talked before. So it seems that for each piece, it may be possible to find a generic form to write this equation in terms of just two coefficients, alpha and beta. And that's what we want to do next. Okay, so this is our approximate solution so far. Let me just finish this up. Very good. Now, what I want to do next is to write all of these in that generic form. And that generic form in this case, if I just think about it, or if you think about it, it looks exactly the same way that we did previously. It turns out that we can write all of this like u equals 1 minus 1/2 alpha plus beta times x plus 1/2 of alpha times beta. And then again, this holds for a piece where x is between alpha and beta. Okay, so all of this, it turns out that it follows exactly this structure. And this is now very nice for us because, okay, this is a 4-piece structure. You see this, but also we see that when we played this 3-piece game, we also saw a similar unified form. Let me see if I can see that. Yes, here. So also for the 3-piece, we had this unified form. Also for the 2 pieces, we had this similar structure. So without doing it, I just write this claim. You can actually do it. But if you do it for not only 2-piece or 3-piece or 4-piece, you can just call it n-piece linear generic approximation. Okay, so this is generic in the sense that the alpha and beta are just generic numbers. Okay, they obviously beta should be larger than alpha and they should be between 0 and 1, but still they don't have to be exactly in the center or 0.4 or 0.3 or anything. They can be anywhere. Okay, That is message 1. Message 2 is if we want to play this game for one, let's say for a specific case. So let's think of a uniform case now. If I just play this for a uniform case, then U would look like 7/8x, 5/8x plus 1/16, 3/8x plus 3/16, and 1/8x plus 6/16. If you look at this now, the first piece is for x in the first quarter, then x is in the second quarter. So it looks like a uniform four-piece. But the reason I'm doing this is that, again, if you look at the coefficients, 7/8, 5/8, 3/8, 1/8, you see that they are decreasing from left to right with, let's say, with the distances of a quarter or 2/8. So basically what it tells you is that if you also plot the U prime again, so if you plot U prime versus X, and then assuming that this is your analytical solution again, and now you have these four pieces which are going to be, let's say, equally distanced. So maybe they are here. If you think of these four pieces, then they would also look like these. So you would again see these little triangles canceling each other. So this would be your 7/8. This would be, I don't know, 5/8, 3/8, and 1/8. Okay, so basically this story of getting zero area or zero difference of area between analytical solution and approximate solution is a thing, is something that we consistently observe. All right, so this was a four-piece solution. Again, if I come back to the menu that we started with, we had done this, and today we also did this, and we did this. Now we want to come to a quadratic version of it. So we want to do one piece, but that one piece is now quadratic, is not linear. Let's see what happens. Now the process is similar to what we did previously, but because it is quadratic, the constraint that we use are slightly different, or the procedure has different coefficients to have. Okay, so we want to do now one piece quadratic. So again, this is exactly the, let's say, the template that we started with. And if it is quadratic, it doesn't mean, or we don't have to say if it is generic or not. It's just one piece. So we want to do one piece, but now that piece is quadratic. And one piece means that the ends are just 0 and 1. Okay, so if I wanted to draw that domain that we always write here, the two ends are just 0 and 1. It's just one piece. All right. Now, one piece means x is between 0 and 1. Now your test function is a quadratic function, so it would be c1x squared plus c2x plus c3. Your displacement would also be a quadratic function. So u would be d1x squared plus d2x plus d3. Now, using our condition, our boundary conditions, again, we can immediately see that C3 is 0 because W at directly boundary condition is 0. We can also see D3 is 0 because U at 0 is 0. All right, so that's that. Now, all you have to do is to write your integral form, your weak form. And it's just one piece, so you don't have to really split it. You would have W prime U prime dx here equals integral from 0 to 1 W dx. So if you look at your functions now, W prime is 2c1x plus c2. U prime is 2d1x plus d2. And W is just what it is. It's c1x squared plus c2x. All right, so what you want to do next is to just integrate this. I will skip the intermediate mathematical steps, but if you integrate that, you end up with an equation which looks like this. C1 times four over 3 d1 minus 1 over 3 d2 and 1 over 3 plus d2 plus c2 times d1 minus 1 over 2 plus d2 equals 0. Okay. And I think in the previous instances, we used a different color for this. So I'm going to use that color to indicate that it's the same equation. So it is 0, but then again, remember we have the same gain here. This should hold for any C1 and C2. So again, it looks like one equation, but because it holds for any C1 and C2, it means that this must be 0 on its own, and this must be 0 on its own. And now, looking at that, that gives you a system which is indeed a two equation, two unknown system. So that's what we have. So if I write that two equation, two unknown system, you would have 4 over 3 d1 plus d2 minus 1 over 3 is 0. And then d1 plus d2 minus 1 over 2 is 0. And then again, this is just a two equation, two unknown, giving you or telling you that d1 is minus 1/2 and d2 is 1. All right. So all you have to do next is to insert these into your U. Okay, so we want to do that. And now I'm using intentionally the color orange because what you see here very soon is that, so you insert this, what you see here is something that you had seen before with, let's say, with the orange color. So u would be minus 1/2 x squared plus x. So this is very interesting because if you look at this, we got this from the weak form. But if you remember, this is exactly identical to the analytical solution. Okay, so this is identical to analytical solution. But make no mistake, this is still the approximate solution, okay? Because we got this from the weak form, okay? We did not use, or we did not take advantage of the analytical solution. So it's still our approximation, but it looks like a very good approximation. So it's still an approximation that has zero error, or it happens to have zero error if you want. Okay, so what do we understand from this? So remember previously, for instance, even if we had the 4 linear generic approximation and it was very long to derive that, you see there are still little differences, okay? But if you look at this one, this is identical to the approximate solution. So what is happening? What can we learn from this? What is the message? The message is simple. The message is, if the space of your solution, if the space of your approximation is large enough, is good enough, if the approximation space, is large enough, it can include the exact solution. Does that make sense? It can include the exact solution. So that's exactly what we see here. Or in other words, what I'm trying to say is that if the approximate solution or the approximate space includes the exact solution, then that error is zero. So basically, that's the key message here. The key message is that what you usually do is that you have this, let's say this is your exact solution. So this is the exact solution space. And then your approximate solution space is let's say a different circle, is maybe here. Okay. Or possibly you can imagine that the circle of approximation, it is smaller than that circle of exact solution. By the way, it could be larger, but it could be out of the exact solution. So being large or small, it doesn't mean that it is. So let's say being large, it doesn't necessarily mean that it's a good thing. You can have a very large approximate space, but it could be here, okay? So this could be your approximate space, but also this one, okay? But this is not good enough. Obviously, you can see if you have a space which looks like this is not good enough. But if your approximate solution was large enough such that it includes the exact solution, then you get zero error. So in that case, let's think of this scenario. And this is what just happened to us here. So this is your exact solution. It just happens that in this particular example, your approximate solution is coinciding with that. Okay, so let me just put that approximate solution or approximation space, let's call it approximation space coincides with exact solution or with this space of exact solution. Again, I'm saying this in a very sloppy manner to convey the message, but you get the idea. Now, what we want to do after this is to play even a more interesting game. What we want to do is to do a one-piece cubic approximation. So we want to do the same task, but now using a cubic function. So we don't have time to finish that, but let me tell you this. So if you use a cubic approximation, and now it looks like that. It feels that you need a quadratic space for your exact solution. So let's call this a quadratic space. Now, if your approximation is cubic, it would be even larger. Okay, so this could be your approximation space now. This is your approximation space. And obviously this is not going to go wrong, because if approximation space is larger, it already contains the quadratic space. So let's say if your approximate solution is something like, I don't know, a x cubed plus b x squared plus cx plus d, obviously what can happen to you is that a could be 0, d could be 0, still b could be minus 1/2, c could be 1, and still this would include the quadratic solution. Okay, so if you do a cubic approximation, and we will do it at the beginning of the next lecture shortly to sort of close this topic. If you do that, you can see that automatically that cubic coefficient, which is not useful, it becomes 0. So it doesn't give you a wrong solution. So any quadratic polynomial is also a cubic polynomial with coefficient 0 in front of the, let's say, the cubic term. So that's going to happen, and I will show it at the beginning of the next lecture. But I think you have the, let's say you have the generic picture now. You have the big picture. So we played with this exercise for a couple of lectures now, and we did one-piece linear, two-piece linear, we did three-piece linear, four-piece linear, one-piece quadratic, and then again, if you do one-piece cubic, and that's very short and simple to do, you can see that basically you recover the one-piece quadratic solution, which makes a lot of sense because your space, your approximate space is large enough, is rich enough so that it contains the exact solution. All right, that was everything for today. We will pick up where we leave off today in the next lecture. Thank you very much for your attention.